Although we've discussed spins using the z representation so far, with eigenfunctions corresponding to pure spin-up and spin-down states, as we mentioned previously, this representation can also actually describe spins oriented exactly along the x-axis, or exactly along the y-axis, or even spins oriented at any angle. A spin pointing in the x direction can actually be expressed as a linear combination of spin-up and spin-down states described in the z direction. How can this be? Note that the spin vector we've discussed so far is not a vector in ordinary geometrical space. It is a spin state vector in a two-dimensional Hilbert space. One way to find the two spin state vectors for a spin oriented in the positive or negative x direction, for example, is to find the eigenvectors of the sigma x Pauli spin matrix. And we could certainly do that. But that might still not resolve our confusion here. Our brains simply can't visualize left and right as being combinations of up and down. In fact, we should not expect them to do that. The general spin state can, however, be visualized in a particularly elegant way. Mathematically, we only need 4 real numbers to specify the electron spin vector. That is, we need a real and an imaginary part, or equivalently a magnitude and phase, for each of the 2 elements of the vector. This does give us enough variables to specify the 2 angles and the complex amplitude, that is, magnitude and phase, for a spin pointing in any specific direction. The connection between these 4 real numbers and the angles and complex amplitude we need is still not obvious, however. We can start by seeing some simplifications here. Since the magnitude of the vector is fixed for spin, the sum of the modulus squared of the amplitudes of spin up and spin down must add up to 1. Then we can conclude that we don't really need 4 independent real numbers to describe a spin state. 3 should be enough. We know also that for any one quantum mechanical state, we can choose the overall quantum mechanical phase arbitrarily without making any difference to measurable quantities. So that's another number we can avoid specifying for most circumstances. Hence, we only actually really need 2 real numbers to describe a single spin state. One convenient way to specify these 2 numbers is through a pair of angles. Angles that will ultimately have a geometrical meaning in spherical coordinates as the usual angles theta and phi that we encounter there. However, to start with, we'll just introduce these angles as convenient mathematical variables. We can therefore write the general spin state as some ket vector S, that is, some coefficient times spin up, plus some coefficient times spin down. Now, here we've chosen to write these coefficients as cos theta over 2 and e to the I phi sine theta over 2. We could write them in column vector form as follows. Now, for the moment, we have not ascribed any physical meaning to theta and phi, although we will find out that they do have a physical meaning. And this is a spin state we could write down a general one, at least within some overall phase factor. We could choose to multiply this whole state here by some other unit complex number. But we won't need to do that here, and we will understand we could do that if we needed to. Now, in this expression we have here, if we were to take the inner product of S with itself, that is, the bra vector version of S and the ket vector version of S, then we would end up with a cos squared theta and a sine squared theta. The e to the I phi would be multiplied by an e to the minus I phi in the bra vector, so that would multiply to 1. So we'd be left with an inner product of S with its own bra vector here, which of course is just the magnitude of S. That would be 1 because cos squared theta over 2 plus sine squared theta over 2 is 1. So the magnitude of this spin vector here is guaranteed to be unity. So we have a normalized vector of unit length. And this additional factor we've put in here, e to the I phi, allows for any relative phase between the spin up and spin down. So, as I said, within some overall phase factor, this is a completely arbitrary spin state here. Choosing different values of theta and phi will allow us to define any particular spin state in this system. Now we're going to ask for the expectation value of the Pauli spin operator, sigma hat here, with such a state S. So here's the expectation value. And we will obtain, as a result, after some algebra, what we will call a spin polarization vector. So this is a geometrical vector, P, with a subscript S here. And, as I said, this is just a way of writing this expectation value of the Pauli spin operator. We'll call that this geometrical vector PS. And it will have three components to it. So I, j, and k are unit vectors in the x, y, and z directions respectively. And the x component of this spin polarization vector here is just given by this expression, the y component by this expression, and the z component by this expression. And we'll work one of these out to illustrate what's happening here. But the result of all of this would be the following. So with our definitions of theta and phi in our choice of the way that we are writing the spin state, this spin polarization vector would be a vector with a component sine theta cos phi in the x direction, sine theta sine phi in the y direction, and cos theta in the z direction. So here's the evaluation of one term explicitly. So we're looking at the x term here. So this is our vector S as a ket vector. Here it is as a bra vector. Note we have the complex conjugate in here as we need. And this is the sigma x operator. So we can multiply this out, multiplying cos theta over 2 and e to the I phi sine theta over 2 into this matrix here gives us e to the I phi sine theta over 2. So that's this vector multiplied into that one. We're just left with this term. And similarly, this vector multiplied into that row there gives us just cos theta over 2. And then we can multiply this column vector and this row vector. E to the I phi sine theta over 2 will give us cos theta over 2 sine theta over 2 times e to the plus I phi. And then cos theta over 2 times e to the minus I phi sine theta over 2 just gives us cos theta over 2 sine theta over 2 e to the minus I phi. Well, we recognize, of course, that this is just 2 times the cosine of phi. So here's our 2 times the cosine of phi. And then if we look at this expression here, we recognize that that is just sine theta. And so finally then, we've evaluated this particular term, and we got sine theta cos phi. And we could similarly evaluate the other two terms in the spin polarization vector PS. Now, this vector, which we can draw in geometrical space like this, is a vector from the origin of some coordinate system, so x, y, and z here, out to a point on a sphere of unit radius, because this is always of unit length. We deduced that earlier. So here's our sphere of unit radius. I've tried to draw an equator round here and a polar circle to indicate the sphere. And this point here is in the center of the sphere. And this vector will have an angle theta relative to the North Pole, relative to this polar axis. And it will have an azimuthal angle, that's the angle round here, of phi. And hence a general spin state S can be visualized in terms of its spin polarization vector as an ordinary geometrical vector here, in spherical polar coordinates with these thetas and phis having meanings. The North Pole here would correspond to P being spin up. The South Pole would correspond to it being spin down. in the z direction. This is called the Bloch sphere, with angles theta and phi on this sphere here characterizing our spin state. And the geometrical x, y, and z directions here correspond to the directions of the eigenvectors of the corresponding spin operators. So if the spin state had been, this would be a spin polarization vector along the x-axis. That would be spin, say, plus x, and spin minus x would have the spin polarization vector out along here. And similarly, for spin plus y, along the y direction, the spin polarization vector would be here, and for spin minus y, if you like, it would be over here.